example, one or two events at that time we were too detailed balance. Then we will check whether the environment is same as thermal environment with the access net.
Yes.
And for example, we will check about in that case 13.6 electron volt. Are there enough thermal electrons or is photon coming? Yeah, those things.
Exactly.
Yesterday we didn't check any of that.
Yeah, we didn't take any of that, but you can check because I mean, you don't have incidents of that kind, right? Because here the only thing that is relevant is when two photons collide or two light particles collide, whether they can produce the pair of these dark matter particles, right? And the only thing that, so first of all, we are assuming that the environment is thermal, right? Which we know is true, right? As far as the light particles are concerned, their environment is certainly thermal, right? And the other thing, as I said, we need the occupancy number of the final states, right?
That is for the sigma, right? You multiply, you compute your T sigma, then multiply by these Boltzmann factors and so on.
Yeah.
Take care whether.
Yes. But that occupancy number, we said that we will not take into account because occupancy number of the final state particles is different for the current case as compared to thermal equilibrium. Because in thermal equilibrium, that number would have been much less, right? In the current situation, that number is not so small. Nevertheless, it's small enough so that that factor is negligible, right?
Which is smaller, thermal or?
Thermal will be much smaller. As you saw, if you assume thermal equilibrium, right, then the actual number will go down exponentially, right? Whereas here, the number reaches the n lambda cube reaches some constant value. Right? But both are small, right? And that's the reason why that effect is negligible. Otherwise, the environment is exactly like thermal environment. Okay. So I mean, indeed, we have to check this, but we suspect it only if there is some event that we can identify, which will make it not thermal, right? And in this case, there is no such extra event. Any other question? Okay, so I think we'll proceed. So we'll just finish the discussion on the axionic dark matter. So there are two things which we left out yesterday. One is the energy momentum tensor, and this I'll write down the expression because it will be also useful for discussing inflation. So we had an action of the form yes, -1, 1, 1. So -1, 1, 1, 1 is the eta mu. So from this we can calculate the energy momentum tensor using Noether procedure. Okay, this I'll write down the expression, but this is straightforward. So T mu nu, which is the conserved charge corresponding to translation invariance, is okay, and then there are other terms. If there are potential terms, it's here. And then using that, we can write down, if you remember, we took chi, the spatial derivative of chi to be 0, because the expansion of the universe smoothens out chi, right? So you say all spatial gradients just go to 0 very quickly after inflation. So we use that. So if you use that, then you find that T00 is half phi dot square plus half m square phi square, and Tij is Gij times half phi dot square minus half m square phi square. And so this we identify as rho, and this quantity we identify as P. Okay, so this is what we used last time. Sorry, all of them are chi. Thank you. And they, yes, chi. Thank you. Okay. And based on this, we said that if we have this oscillatory form, okay, it's space dependent, independent, right? So it's like a harmonic oscillator. The chi equation of motion when there is no damping is like harmonic oscillator. So using this, we got that rho is half chi 0 square m square, and P is half chi 0 square m square, and I think you get cosine 2 mt plus a. Okay, basically you get, for rho you get sine square of this plus cos square of this, whereas for P we get the sine square of this minus cos square of this, okay? That's what produces this cosine of 2 of this, and then this means that the average of P is 0, okay, whereas the average of rho is non-zero. Average over time, yeah, because average over, I mean, this is the region where h is much smaller than m. Okay, so in one Hubble time it will perform many oscillations. Okay, so you can average over time, and that gives you average P is equal to 0. So this is the reason why it behaves like a matter, right? Because matter has rho non-zero, P 0. Is this clear? Yeah, this is coming from quantum fields.
It won't be like a paradigm matter is a radiation domination. That matter.
Yes.
So non-relativistic it will have.
Yeah, here, okay. I mean, if we only include this, right, then of course it's a free field, right? So it will be collisionless, right? But of course there are other terms in the action. Quick interaction, yes. So the one point is that this seems to be somewhat different from the dark matter that we use, because for the WIMPs, because in that case you had some massive particles which are responsible for the matter, right, for dark matter. Here it looks like you have some field, right? It's a coherent oscillation of the field that is responsible for matter. But this can in fact be given an interpretation in terms of particles, and that basically comes from the following: that this is like a harmonic oscillator, right? Classical harmonic oscillator that we are using, that's the picture we are using. But a classical harmonic, in a harmonic oscillator, classical motion can be described, can be given a quantum description as a coherent state in quantum theory. right? And those typically take the form e to the alpha a dagger on the vacuum, okay, where a dagger is a creation operator, and alpha is large. Okay, alpha has 1 over h bar, and hence is large. Okay. So if we expand out the exponential, okay, it would look like a highly excited harmonic oscillator, right? If we expand out the exponential as sum over n alpha to the n over n factorial a dagger to the n. For large alpha, this coefficient peaks around n equal to alpha. Right? This is just a property of the exponential expansion. Right? You can use Starling's formula to say for which n is it maximized. Right? It's of n of order alpha. So this basically means that the coherent states can also be thought of as a quantum state containing large number of oscillators, right? Highly excited quantum state. Okay, and that's what we expect. A classical state should be a highly excited version of quantum state, right? Because classical energies are large. So using that, we can also give an interpretation of this, okay? Because this is like a harmonic oscillator, and from quantum field theory, you know that there the A daggers are the particle creation operators, right? A dagger is once you quantize a field as a set of oscillators, A dagger is like the particle creation operator, okay? And in this case specifically, because this is a space independent mode, right? This particular mode doesn't have any dependence on the space coordinate. Okay. This means that these are creation operators for zero momentum states, right? Because k equal to we have k equal to 0. Okay. So in QFT of phi, the element A dagger creates zero momentum chi particles. So we can interpret this collective motion, right? This coherent motion of the chi field as, so the axionic dark matter can also be thought of as a large number of zero momentum chi particles. Yes. So which you expand in Fourier modes, right? That means that the Fourier mode has a delta function at vector k equal to 0, right? So you only have the zero momentum modes excited, right? And that's what so these A daggers should correspond to zero momentum creation operators for zero momentum states. Okay. So we can reinterpret the axionic dark matter as large number of zero momentum chi particles. Is this clear? Because classical state, if you try to represent as a coherent state, right, you find that alpha goes as 1 over h bar. Because in the expression for the energy, suppose you try to calculate the expectation value of the energy, right? In the expectation value of the energy, there is an h bar square over 2m, right? Yeah. Or if I use the creation annihilation operator, it's h bar times a dagger a, right? So the classical state has energy independent of h bar, right? It's a classical energy. So something has to cancel that h bar, right? And that's why alpha has h bar power in the denominator. It could be either h bar or maybe it's 1 over square root of h bar, that one has to check, but it goes to 0, goes to infinity as h bar goes to 0, right? So coherent state has large powers of h bar in the denominator, right? And that's the reason why it's large number of particles. Because otherwise you will not be able to build up the energy, right? A classical energy. And the same thing is true here, that you have some classical field energy, right? A single quantum of field is not going to build that energy. energy, right? Because skies are supposed to be very light particles, right? So you need a lot of them. So the same energy density, we can now reinterpret this as coming from a large number of highly non-relativistic chi particles. Okay. And because it's highly non-relativistic, that also provides a equivalent explanation of why this is pressureless. Right? Because pressureless means that the momentum should be small compared to the energy, and these indeed have that property. Okay. And this also allows you to choose the masses of these chi particles, okay, to be much lower than the energy scale where it's supposed to be non-relativistic, right? Because you saw that around 10 to the minus 2, 10 to the minus 3 electron volt, the particles should have been non-relativistic, otherwise the structure will not form. Right? Structure formation requires that particles should have been non-relativistic at the time of structure formation, right? That's a low energy scale. Okay. But this is saying that the chi particles are naturally non-relativistic, right? As long as these particles are thermally decoupled, right? We have to assume, of course, that the interaction of the chi particles with photons is weak, okay? So that they don't thermally equilibrate afterwards, right? Once they remain frozen, right? They just remain frozen into non-relativistic state. Then even if the chi particle masses, right, are very, very low, say 10 to the minus 15 electron volt, okay, that may still be okay, right? Because they still remain non-relativistic because of this feature. Is this point clear?
How alpha being order 1 by alpha? The argument is because for this state to describe the classical particle, alpha has.
Exactly, that's right. Because it's describing a classical field, right?
Right.
Yeah, so for a single harmonic oscillator, indeed, so in order for it to describe a classical particle, alpha has to be big. Okay. In this case, the notion of classical particle is classical field, but you are only looking at the zero momentum mode, so it's as good as a particle.
And we are getting that by calculating the expectation value of energy.
Exactly.
That comes out to be some h bar alpha.
Exactly. That depends on how far this chi zero was, right? Okay. That depends, of course, on the history of the universe and which part of the universe you are stuck. Right? But this part of the analysis is just a classical field theory analysis. So there's no h bar in this part of the analysis.
And energy is supposed to be order 1 unexpected.
Yeah, exactly.
The set of particles will always froze with the universe.
Always?
Just frozen with the universe. Once it is there, it is.
Yes, exactly.
So does dark matter really have any kind of movements as such in the galaxies?
Yeah, they have gravitational movement, of course.
So that gravitational movement is possible for
Yes, because everything gravitates. So there is no option of not coupling them to gravity, right? Because square root of minus determinant g is there, right? There is a g mu here. So these particles are all coupled to gravity exactly in the same way, right? But other than gravitational interaction, right? Any other interaction should be weak enough so that it doesn't destroy this zero momentum condition.
Coupled to photons via gravity. But it's not.
Well, no, not necessarily. There are couplings of axion. Conventional axion have a coupling to photons, but the coupling strength is small. Okay? So this is the limit you have to put. That whatever serves as the axionic dark matter should have sufficiently low coupling to the photons so that they don't equilibrate.
But how low? I mean, can we see?
Yeah. So in fact, there is a paper, which unfortunately I'll send out on the email, which there's a recent paper, or not recent meaning, maybe 4 or 5 years ago, right, which summarizes the limits on axionic dark matter, right, how light it can be, and if I remember correctly, it can be very, very light, like 10 to the minus 20 electron volt even, that is allowed, I think. It is.
So its interactions with all the standard model particles
Will have to be small, exactly.
But how do you, how do you bound them?
How do you bind? Okay, you cannot just bind M, but M together with the couplings, you can bind. Right? Like for example, one of the kinds of bounds which came is for the stars that if these particles are there and if they have whatever their coupling is with the standard model, there is always a probability that the particles will be emitted by the star, right? Because interactions are happening. Say the sun, right? And then you have to see how much energy, given the parameters, how much energy the sun will lose, right? And that puts a bound, because if sun loses too much energy, then it will not be what it is, right? So that, in fact, originally some of the bounds came from observations of that kind.
There we said like these guys have to go out of equilibrium very early and not relativistic.
Yes.
Here it's non-relativistic.
Yeah, it's not relativistic.
They went out of equilibrium very early because they were very massive.
Exactly, yeah.
Here these are very light.
No, neutrinos are not now massive.
No,
The weak interaction, W and Z bosons are massive.
no, these beams that
WIMPs, yeah. They went out of equilibrium because their interaction was weak, right?
here also interaction is weak.
Yeah, here also the interaction is weak.
Their interaction was weak and they were very.
Yeah, the fact that they are very massive is no, it's not the same. I mean, WIMPs means massive particles. The M there stands for massive, right? So the WIMPs, like dark matter, right, is for particles of order 100 GeV or more, right? And that, as I said, came more from the particle physics motivation, right? Because if you just forget about particle physics, right, then there is a wide range of dark matter particles that you can allow, right? But from a particle physics viewpoint, right, these weakly interacting massive particles appear naturally in various extensions of the standard model, in particular supersymmetric extensions. Okay. And these axion fields also come in some aspects of particle physics, because when you try to explain the CP or approximate CP invariance of the strong interaction, okay, then you invoke these axionic particles.
And these dark matter candidates, all of them has to go out of equilibrium very early.
Well, not necessarily. Dark matter candidate, for example, could be like protons, that some excess was produced. Suppose there is a conserved charge, and some or approximately conserved charge in the standard model, but some excess was produced early in the history of the universe. Then that will be frozen, right? Whether it goes out of equilibrium or not. Because excess you cannot destroy.
Okay, they go out of equilibrium very early.
Yes, they will go out of, because their interaction is weak, right? We have already assumed that this fact that there is an approximate shift symmetry, right, tells us that interaction is weak. That chi goes to chi plus a constant.
At the master value.
Yeah, so mass term violation, that's why mass has to be very small, right? It's an approximate shift symmetry. But any other coupling to any other field also has to have this approximate symmetry. So the couplings of these fields are small.
So why do you say that there's an approximate CP for the strong interaction?
Oh, strong interaction, because the point is there is this, because of the, there is a term that you can add in the strong interaction Lagrangian, is theta f mu nu, f tilde mu nu, right, which violates CP.
This is the F at Jeff term.
Yeah, the FHF term, the strong CP. So this is what is called a strong CP problem, that if theta is not 0, right, if theta is equal to 0 and pi are the CP invariant combination, but if theta is either of those, okay, then it's not CP invariant, and you should have seen it in properties of protons and neutrons, right, but you don't see it, and so one has to explain why theta is close to 0. Okay. And there the idea was that the theta actually is controlled by the vacuum expression of chi and of the axion, right? And the minimum of chi is at 0, so that eventually when chi settles down to 0, theta will effectively theta will become 0.
But from this point of view, why should theta not couple to the other, for example, the matter sector of the standard?
No, here theta is just a constant. In the usual QCD, theta is just a constant. You can add this term, right?
I can make it a field, right?
Yeah, you can make it a field, right, which is chi, right? Then you call it chi.
Yeah. That's why I'm asking. So why wouldn't chi couple to the matter sector of standard model?
Because if it does couple to matter sector, right, then it violates, meaning you can observe it, right?
Okay.
So you know that the coupling has to be very small. And basically this in that picture, the effective coupling of chi is generated dynamically by the QCD effects. But now this axion is used for very many other contexts, right? Original QCD axion, that's not the motivation anymore, in the sense that I think QCD axions cannot really solve this problem, right? Because there is a strong constraint on the parameters of the QCD axion. And as far as I know, that has the QCD axions being dark matter candidates has already been ruled out.
Where do those constraints come from?
Which constraints?
The axion, the coupling constraints from QCD.
Because QCD axions will have very specific coupling to the standard model fields, including the photons and the gluons, right? And then, for example, in the sun, they will be produced, right? By the strong interaction effect. So the QCD axion, if you are trying to use theta to solve QCD theta problem, right? Then its couplings are not completely arbitrary anymore. There are some couplings that you have to have.
You're saying there should be couplings with the matter that you have to have.
Like this. This is coupling to gluons, right?
Sure.
Okay.
But this you will see what
There will theta will be replaced by chi, right? So chi with two gluons, right? Inside the sun, right? All the strong interaction processes are going on, right? So there are lots of gluons in the sun, right? And during that process, you can emit chi.
And we should have seen it is here.
Exactly. We should have seen it, or it will lose energy fast enough so that that it will just start losing energy fast enough.
So the QCD theta does not explain dark matter.
Exactly. Yeah. The QCD theta does not explain dark matter. I think that's the point. I mean, so there are various windows, right? It can be either very strongly coupled or very weakly coupled, and I think both windows have now more or less gone. But massless scalar fields appear in many other contexts, right? So, I mean, so axionic dark matter is some candidate massless or nearly massless scalar field, right? Which has also very little coupling with the rest of the particles.
How this will explain the current observation of that 35%?
Well, that percentage will depend on the parameters, right? The energy density that you calculate will depend on this chi 0 and m and so on.
So some combination of these should be determined as gravitation.
Yes, indeed. So some combination of these, right, will be determined from current observation.
So this mass also we can only get in EV. Some of them.
Yes, exactly. Right? Usually people use some kind of cosine potential. Cosine, right? Where, and then you can try to put constraints on the parameters of the cosine potential. Okay, so I think this is as much as I'll talk about dark matter. Now we'll switch to inflation.
This chi naught is the same as the chi naught that it froze to pre.
Yes, exactly. It is the same as where it froze to during inflation in our part of the universe, right? In another part of the universe, it may have a different value.
And this mass of the chi can depend on temperature with time. So then it will become a function of time.
Yes, but if it is very weakly coupled to the standard radiation, right, then the dependence on temperature will also become low.
And this assumption about chi being spatially homogeneous, say if I corrected it, how strong would the corrections be? I mean, how significant would the correction be?
Well, that will mean the non-zero momentum modes will be excited, right? Then it's no longer true that it will behave like a matter, right? Because now P is also non-zero. Because matter means P equal to 0, rho non-zero, right? If it carries non-zero momentum, or gas for example, right? A gas has pressure and energy density.
Yeah.
Right? Energy density of course far exceeds the pressure because the motions are non-relativistic, right? But imagine that there is a K which is of order m, right? Especially in homogeneity. Then when you give a particle interpretation, it's like particles moving at relativistic speed, right? Or speed of order 1.
And that's not
That's not good because that will mean P and rho both non-zero. Right? Dark matter we know has P equal to 0. Okay, this is the statement that at the time of structure formation, right, it should really behave like matter. It should be non-relativistic.
There's some argument, okay, maybe I missed something there. There's some argument for why dark matter has to be non-relativistic.
Yes, and that means zero pressure.
Yeah, that means zero pressure. I mean,
Yes.
that was a fact.
Yeah, yeah.
Which is why you're saying you should have zero pressure. But what is the argument? That
Oh, the argument is that if it was relativistic at the time of structure formation, then structure shouldn't form. Well, the kind of structure that we see wouldn't form, right?
structure is dark matter structure.
No, just ordinary, I mean, what you see in the stars and galaxies, right? So the idea is that those structures formed by gravitational clumping, right? And gravitational clumping is less efficient for relativistic matter. Right? For example, if you assume that there is no dark matter, right? Only matter, 5% matter, and you try to see how, if we now run your computer code and see whether the structures could form by the time we are seeing it, you will find that it wouldn't form. That it's just slow. Right? No, even non-relativistic matter, but only 5% is not enough, right? You need enough gravitational interaction, right? Because we already know that at the time of CMB, the fluctuation was 1 in 10 to the 5, right? From there, it has to grow to what we see today, right, in the universe. So you have to have enough gravitational pull for such structures to form, and that is less efficient if you have relativistic matter. Right? Because relativistic matter tends to move fast, right? So if you try to form some structure here, it will carry away that information somewhere else and try to uniformize the system. Yeah, so that's the argument that dark matter has to be non-relativistic at least at the time of structure formation.
So only axion zero modes are physically relevant. Only zero modes of the axion.
Yeah, only zero modes of the axion are relevant, right? They are the ones which contribute to the dark matter. Any other question?
Based on winds, we did some detailed balance calculation. And
Yes.
Trying to see, like, independent of observation, we were able to see that okay, this eventually it will give the current value of observation.
Well, we have to put the parameters, right? Sigma and V.
That is we calculate from the microscope.
Yes, exactly. So here also, once you know the microscopic theory,
Oh, that we don't know.
well, this is the microscopic theory. You also have to know the chi0, right? Where you started. Then you can calculate the density.
Then at least some parameters should come from the observation.
Yes, exactly. Yeah. So here, if you know the microscopic theory, right, we still have to know the history, right? That how big chi0. See, we would expect that unless our universe is somewhat special, right, the chi0 would be of the order of the fluctuations that you had in the early universe, right? And that, in principle, can be determined from microscopic theory, right? Just follow the whole history of the universe, and imagine that the chi0 has some kind of sinusoidal wave, right? And then you will expect that the amplitude, the value of chi0 at a generic point, would be of the same order as the amplitude, right? As the maximum, unless we are very special and we are sitting near the node, right? It will be of the same order. So you cannot determine chi0 exactly, but order of magnitude you can determine if you know the microscopic theory and if you knew the history of the universe.
History as in pre-H.
Exactly. Pre where this thing happened.
But at some point it is like whether not in our universe, in some universe it is possible to have chi0 is equal to 0.
Yes.
So then it is p equal to 0, or equal to 0 is that.
Yeah, so that universe will not have dark matter. Yeah, and if it doesn't have dark matter, it will not have formed structure.
Even at some later stage, not.
Yeah, at later stage maybe it will, but if you also have the cosmological constant, right, then what would happen is that by the time they start clumping, right, the expansion of the universe will become so fast that it will pull them out. Right? So there is an optimal window. Even in our universe, there is an optimal window in which structure could form. Right? If the structure hadn't formed by now, right, now the universe is accelerating. Right? So the things will get diluted very fast.
So universe without dark matter will not have structure.
I think in our universe, without the dark matter, we will not have the kind of structure that is needed for formation of stars and galaxies, right? It will have some structure, of course.
So when you say our universe, you're specifying the cosmology.
Yes, exactly.
So given
That time we will have to compare the gravitational collapse with the effect of expansion. Right?
Exactly.
The gravitational collapse is large.
Yeah, but for gravitational collapse to be large, right, you need large density fluctuation, right? We already know at the time of CMB the density fluctuation was 1 in 10 to the 5.
That's why we need to compare.
Yeah, exactly, right? So 1 in 10 to the 5 was there at the time of CMB, right? Now the question is whether today just matter would have been enough to form the structure that we see, right? Starting from that 1 in 10 to the 5 fluctuation there.
Yeah, but not these kind of structures. That is, if dark matter was not there.
Yeah, if the dark matter was not there, it will not be structures that we of the kind that we see. Okay, any other question?
and these two are the only the rims and axioms are only the only
I think these are the only popular ones, right? I think there are many others. Because if you if you exclude particle physics, right, then there is a whole range, right? You just have to somehow produce a non-relativistic particle, right, which is undetectable, which in today's experiment, which would not have been detected, right? And there are probably many candidates that you can.
we can't say undetectable without standard models. Right? We are all standard models, so we can't detect something if not interacting with standard models.
Exactly. Yeah. True. Right. But if it's not interacting with standard model, you have to also explain how it was produced. At some point, it should have been produced. Right. But it's true that if it's suppose it only gravitates, right, and it was somehow produced in the early universe, right, then because you have not seen dark matter interacting with anything, right, that would have been a perfectly sensible solution.
But when we account for the standard model, we are the only ones that are consistent.
No, I do not say it's these two only ones is consistent. Even if you have the standard model, that you are not touching the standard model. Suppose you add another field which only couples gravitationally, right? That field could have served as a candidate for dark matter, right? Suppose there are some massive particles of those, that field was produced somehow in the early universe. They would gravitate today.
But then there is no reason why that field should not interact with the standard model. Right?
No, in a Lagrangian you can write a term without coupling, right?
Yeah, but then QFT will make things run and give extra terms which couple this to everything else. Right?
Well, QFT will run via gravitational loops.
Yeah.
If you don't have,
Those are suppressed.
yeah, those are suppressed, right? Of course, in non-renormalizable theory, you have to worry, right? But if you have a finite theory, suppose you have a string theory which has two sectors, right, which don't talk to each other, right, except gravitationally, then you could have very low coupling between these two systems, right, and that could serve as a dark matter candidate.
So why is that not an explanation?
No, it could be an explanation, right? So that's why I'm saying the dark matter, if you don't say that you want to also include that if you wanted to do something more than just producing dark matter. See, these are popular because these in principle do something more than just producing dark matter, right? WIMPs, for example, are natural in supersymmetric theories. That once you have a supersymmetric theory, you automatically get candidates of that kind.
So why is this simple extension not accepted? I mean that.
No, it is accept. I mean, there's nothing wrong with this simple extension, right? Either this simple extension requires that you are adding this extra particle just to solve the dark matter problem, right? Okay. Whereas WIMPs, for example, right, are there in supersymmetric theories. You don't have to add this to solve the dark matter problem, right? If you have a supersymmetric standard model, it automatically has candidate massive particles which are stable or with a very long lifetime.
But if you add this particle and it is internally consistent, and if it's
yeah,
externally consistent,
there's nothing wrong with that. There's nothing wrong with that, right? So dark matter candidates could be just some particle that interacts only gravitationally and nothing else. Right? As long as the history of the universe allows the creation of such particles. See, it need not even be dark matter one particle, right? There may be a dark sector. That whole another dark QCD, dark weak interaction, everything else, right? which we don't interact, right? And in that, somehow some matter got created, right? Maybe they are the protons and neutrons of that hidden sector. Okay? That's also certainly perfectly possible. Because today we only know existence of dark matter through gravitational interaction. There are many string theory, solutions with this kind of property, that there are two sectors which are decoupled. Right? So that other sector could be the dark sector.
Decoupled but coupled to gravity.
Through gravity, exactly.
Then you can add anything you want in the dark sector.
Yes, you can.
Have an arbitrary gauge group.
Yes, indeed. Right? So for example, some string theories have a gauge group which is product, right? And particles don't have representation of both. Right? They are either in this sector or in that sector. So those kinds of theories, right, will have that, their QCD and our QCD, right? And they have no interaction except through gravity. Yeah, so that's also perfectly allowed.
And then the suggestion that the gravitational loops are suppressed. This can also break at some point, right? But I guess you have to go.
This can break at some point, but in string theory, it normally doesn't happen. Right? If you have interaction only via gravitational loops, right, they remain decoupled because it's not normalizable theory, but it's still, you can do this calculation through string interactions. Right? That interaction remains suppressed. And you can make it small enough so that you wouldn't have seen the other sector.
But why were you saying they only interact through loops?
Because at tree level, it's like two gauge groups, right? And there is no particle which carries both representations, right? So Lagrangian without gravity will be a sum of two Lagrangians, right, which have no coupling at all, right? So the only way these two Lagrangians couple is because both couple to gravity. Yeah, because this coupling, square root of minus determinant G and the G mu, that you cannot avoid, right? That's general coordinate invariance. So through gravity they will couple. And that's why you are seeing the dark matter. The classical aspect of that is that we see the dark matter because they also gravitate.
It was really interest to us to have multiple particles in the dark sector, which is only interacting with our sector through gravity, to have multiple particles and have interaction.
Yes, it is possible. Meaning,
No, it is of our interest.
it is of our interest. Meaning, okay, if it happens, it will be of our interest, right? It will not directly affect anything that.
Can we have observations for that? Can we have effects of those things?
Not a direct effect. See, if we could solve the dark sector completely, right, and predict what kind of dark matter, what kind of matter density it will have. Of course, so the point is one dark sector, right, how much dark matter there is, will be determined by the physics in the dark sector, right? So in that sense, it's interest. If you want to predict, for example, how much dark matter there should have been, right? We know it's 25%, but can you calculate and see that it is supposed to be 25%, right? So for that, you need to know the physics of the dark sector, what kind of interaction it has, and so on. Right? But if it only coupling to us through gravity, you will not have a direct observation of that sector.
On the observations, can we put some bound on the strength of interactions of the dark sector, because
it puts lower bound. Yeah, upper bound, that the strength of interaction is less than this because you have not seen it, right? But because you have not seen it, right, the interaction strength could even be 0, right? The non-gravitational interaction strength. Yeah, so the upshot is that you cannot really say very much about dark sector, right? These are popular candidates because these come out naturally from other particle physics scenarios. Any other question?
So in this axionic case, we have rho, right? Density.
Yes.
So we will use
some formula and then evolve it, make this dark matter decouple and then match the
Yeah, dark matter would have decoupled very early because we have already assumed that the M is small, right? And any interaction has to be small because you demand this approximate shift symmetry of chi.
because it is non-relativistic, equilibrium non-relativistic equilibrium formula will follow, density will decrease and
Yes, so density will follow as 1 over lambda cube, right?
when it is decoupled.
When it is decoupled. And the decoupling happens very early because, as I said, that its coupling to everything should be small, right? Otherwise the shift symmetry will be destroyed, right? See, if there is a coupling of the form chi times something, right? That will not be invariant on chi going to chi plus constant. So axionic dark matter by construction has to have weak coupling to everything.
As temperature decreases, what happens?
It decouples very early and then it just continues to, the density continues to fall as 1 over lambda cube.
We can also say that it should decouple early because it is non-relativistic and
Yes.
suppose, and it is in equilibrium. So the density, number density, goes as e to the minus m by t.
But here you are talking about fields, right?
Yeah.
M is very small. M can be 10 to the minus 20 electron volt, as I said, right? So that argument is not the reason why the density is not going down. Here it's decoupling because the interaction strength is very small, right? So the axionic dark matter by definition has very low interaction with everything, at least with all the standard model fields. Right? So from very early in the history of the universe, it would have not exchanged energy with the standard model fields, because if it did exchange energy, right, then it will not remain in this form, right? It will get destroyed. This profile itself will get destroyed. Right? So it is necessary that the axionic dark matter should have very low coupling to other fields. Okay? That's why this approximate shift symmetry is needed.
You concluded for the early universe, when n is much less than h, that chi has to be this constant chi 0.
Yes.
By studying the axionic equations of motion.
Yes.
In that limit. So you basically get chi double dot plus 3h chi dot equals 0.
Yes.
But then that's a second order ODE, right? So it should have two solutions. So the constant is a solution, but then it also has another solution, right? Why did we discuss that one?
Well, h is big, right? So the natural solution, so chi dot is constant, any constant, right? That's what we mean.
Chi dot is constant is not a solution.
Chi dot is 0 as a solution, yes. Yeah. So what is the other solution?
1 by a cube is a solution of that.
Yeah, but that requires a very fine-tuned initial condition. It's like you have to start with a very, think of a very viscous liquid, right? And a gravitational force, right? This has again second derivative equation of motion, right? If you have a particle moving in this viscous fluid, but for any natural boundary condition, if you drop a particle in the viscous fluid, right, its velocity is very, very low, right? And that's the solution we are using. As opposed to high velocity, right? We are assuming chi dot is small. So basically it will get damped, right? The whole idea is that eventually, whatever solution you start with, it will eventually approach a solution where chi dot is very, very small. Right? So even though it's a second order differential equation.
But you're saying that, I'm discarding the boundary condition where I start with an extremely high velocity.
Exactly.
And what does that mean? You're discarding the boundary condition that...
to begin with, chi dot was very, very high, right?
Why?
Well, there is no reason why chi dot should be very, very high, right?
There's no reason why chi dot should be very, very small.
Well, I mean, a range of order 1 is the natural range, right? If you assume that some field has a very high time derivative, right? You have to give an expansion of how did it occur such high time derivative, right? because it will typically have chi dot, which is the natural frequency, right, which is controlled by m. Right, and in any case, the point is if it continues for long enough time, right, during inflation, for example, right, where h was constant for a long enough time, it would have eventually damped. Right? However high velocity, exactly, it will eventually reach a terminal velocity, right? And the idea is for large h, the terminal velocity is very small. Any other question on this?
So the statement is that I can start with arbitrarily high dot, but then it will soon enough.
As long as the inflation lasted for a long time, it will damp it out to its terminal velocity.
Because of the large value of the Hubble.
Exactly, because of the large value of the Hubble constant. Okay, so let me at least start with the classical part of inflation. This will be more like a review of what we have already done in GR. So we review the horizon problem. So the FRW metric was minus dt square plus d plus lambda of t square dr square. Okay, I'm assuming flat universe. Okay, but this can also be easily generalized to non-flat universe where you put that k factor in. So if we take a radial light ray, okay, again radial doesn't really matter because it's homogeneous and isotropic anyway, right? But let's suppose we take a radial light ray, then it will follow the path, the dt square is lambda t square dr square, and this tells us that dr is dt over lambda t. So now the total distance traveled by light, total distance traveled by light from Big Bang. So in this case, Big Bang are defined to be the lambda equal to 0, right, to some time t will be given by RH as integral 0 to t dt over lambda t. And now you want to change variable to lambda prime, which is basically lambda of t prime. This is the total distance in today's co-moving horizon. So this is a co-moving horizon. So this is co-moving horizon in today's distance. Okay, physical horizon we can calculate by multiplying this by lambda of t, but we will not do that. Okay, let me write t prime here. If you change to lambda prime, then RH takes the form integral 0 to lambda d lambda prime over lambda prime times lambda dot t prime. It's clear, we are just using the fact that d lambda prime is lambda dot t prime dt prime. Is it clear? So in the standard FRW cosmology, we can calculate this, okay, for various values of lambda, right, at different times. And the problem that we had found is at the time of last scattering, that imagine that this is the last scattering surface. This surface we know very well where it is, right, and how much is the radius, the co-moving radius of the surface we know, because determining this only requires physics between last scattering and today, right, and that we know very well, right. So you can reconstruct back. So this is about lambda s of order 10 to the 3, 10 to the minus 3. Right, you saw that the temperature at which last scattering happens, right, was something like 3000 K, right, and that's about lambda equal to 10 to the minus 3. Okay. So at lambda is equal to 10 to the minus 3, what we found? So we found that RH at lambda equal to 10 to the minus 3, this spans 2 degree on the last scattering surface. Okay, so if you take 2 points on this last scattering surface, then if you take any one of those points and see how far you go, okay, when you travel a distance of RH of lambda s, that's about 2 degree in the sky. This means that anything outside 2 degree, right, from between here and here, for example, or between here and here, there would have been no light travel from the time of the Big Bang till the time of last scattering. Okay. And that was a problem, because if they had no communication, right, then that means, so if there is no light travel, then that means there could have been no communication. Okay. And if there is no communication, then it will be hard to explain how the initial conditions got uniform, right, because you know that the temperature fluctuation is 1 in 10 to the 5, right. If you look in this direction versus this direction, the difference in temperature is of order 10 to the 5, 1 in 10 to the 5, right, 10 to the minus 5 of 2.73 Kelvin. Okay. So this has no natural explanation in standard FRW universe, because these points were never in communication at the time of last scattering. Is this point clear?
At lambda equal to 0, all these points were at a point.
Well, you shouldn't think of it that way, right? Their physical distance was 0, you can say. You think of these points all as separate, right? Lambda equal to 0 means the metric is going to 0. So in that sense, the physical distance was 0. But don't think of these as points being together, right? Think of the manifold as the whole manifold, right? Their physical distances were 0, right? But don't start at lambda equal to 0, let's start at lambda equal to whatever small number you want, 10 to the minus 20, 10 to the minus 40, right? At that time, these points are separated, and you're starting to count the light travel from that time, right? And the point is, between that time and last scattering, light would have traveled only a very small distance compared to the size of the last scattering surface. Yeah, so that is the horizon problem. Right? The horizon was too small to explain the uniformity of the microwave background.
This started with same initial conditions, but they not have independently evolved with the same.
Yeah, so the point is when you say started with same initial condition, right, then that's not natural. Who sets the initial condition, right? Why did they start with the same initial condition, right? I mean, it will be much more natural to explain how it became uniform, irrespective of what initial condition you started, right? Because for most of cosmology, as you saw, right, the initial condition really didn't matter because thermal equilibrium uniformized it, right? But the point now is that the thermal equilibrium unifies over small scales, right, but not over scales of this kind, right? The far away points on the large scattering surface. Right? So if effort, the standard FRW would have been true, right? Then what we would expect is that in this part there will be some temperature, in this part there will be some other temperature, right? There will be some fluctuation of order 1, right? If we are saying 2.7 in one direction, maybe it will be 5 in another direction, 1 in some other direction, and so on. That's a natural fluctuation again, right? You don't want to introduce other small or large numbers, right? So the fractional fluctuation should be of order 1, say, right? When Gautam said that would have been a more natural expectation. Is this okay? So the solution that inflation offers is the following. Is to change the history of the early universe
So before this, we have calculated the rate of reactions and we have compared the rates of reaction and the rate of expansion, right?
Yes, exactly. So all those have to, so whatever happened in the early universe had to happen before that, right? If you want all our calculations to be preserved, right, like Big Bang nucleosynthesis, we did the calculation, right? So early universe means it should be before the Big Bang nucleosynthesis.
No, I'm talking about nucleosynthesis and baryosynthesis, okay. All other events that happened after the early epoch era is okay.
Yes.
I'm asking, in the early epoch, we are expecting to have a thermal equilibrium which will take universe to a fate, which will not depend on the initial conditions.
Yes.
So I'm asking that thermal equilibrium, will it? Have we checked that it will be established? Right?
Yes. If they, okay. So this problem is, this is saying that the thermal equilibrium, right, formula you cannot apply over long distance scales. Right? Within the horizon scale, you can assume that there will be thermal equilibrium because the reaction rates you have checked. Right? But you shouldn't use thermal equilibrium over super horizon scales. Right? Because over super horizon scales, there will be another temperature. It will also thermal equilibrium. Right? But the temperature from in this region and that region will be different. That's in the thermal equilibrium, we didn't determine what the temperature would happen, right? We determine it only by going backwards from today's temperature.
That is fine. I'm actually looking at a patch which is inside of which there can be equilibrium.
Yes.
It is inside horizon.
Yes.
The size
Fine.
of the
Yes.
horizon is bigger than the patch.
Fine.
that I'm looking
Okay.
at.
Okay.
Now I'm asking the question whether thermal equilibrium is possible there or not.
But that you have already checked, right? The reaction rates will be larger, faster than the expansion rate.
Yes. So, but in early universe we have not checked, right? We have not done.
No, at every time when you check thermal equilibrium, we did check, right? Neutrino decoupling, for example, right? We saw that above 1 MeV, neutrinos were in thermal equilibrium because the reaction rates were fast enough.
So in that era we have checked that formula.
Yes.
Before that.
Before that, it doesn't matter. Even if it was not thermal equilibrium before that, right? As long as there is one patch in which it can thermally equilibrate, then initial information will get wiped out, right?
If there is one instant where there was thermal equilibrium,
You can start from there and evolve forward.
for that,
Before that, it didn't matter, yeah.
condition was it won't matter.
Exactly. Right? So that is the whole idea that if you once you have a thermal equilibrium, right, then what happened before that gets wiped out. Right? Because thermal equilibrium essentially determines what happens. Right? Only some things which cannot be changed by thermal equilibrium, like excess baryon density, for example, right? That you couldn't change by thermal equilibrium. So those things will remain. Right? Everything else will go away.
So in this theory, we are trying to get evolve the universe such that at the times we have checked the thermal equilibrium, at that time the thermal equilibrium is established.
No, that we are not trying to check. Yeah, we have already checked those. We are not going to do that now.
We are trying to reproduce those using this theory.
No, we are not trying to reproduce those. We are trying to now explain how come thermal equilibrium exists over large scales, larger than the horizon scale. Right? The fact that within the horizon scale thermal equilibrium will be established, that calculation you have done.
And it gives some fate of the universe.
Exactly. But that depends on the temperature. Right? So the temperature at that time we reconstructed by evolving backwards from today. Right? If today the temperature was different in different regions, then we would have different fates in different regions. Right? Or there will be time lag between what happened here at some point versus what happened there at some point. Right? If something happened here, then something will happen there only when the temperature of that region comes down to the temperature of this region. Is this clear? Yeah, so this is the issue that the horizon scale at the time of last scattering was too small to explain why there is uniformity over the whole last scattering surface. What lambda you used to do this calculation? Oh, this is, we know the temperature at which the electron and proton combine, right? So that's about 3000 K. So that corresponds to lambda equivalent to -3, right? Because today is 2.7 K.
How did you get the 2-degree number?
Oh, because you can calculate RH based on the standard FRW by doing this integral, right? And you can calculate the radius of this, the co-moving distance to the last scattering surface.
Yeah. I'm missing something very basic.
Yeah.
What lambda do you put into that integral?
Oh, this is lambda that you call, reconstruct from today. Today lambda is 1 and we know the standard history of the universe. So that is the lambda you put in, right? That it was matter dominated, radiation dominated, etc., right? That, the point, it doesn't really matter as long as it's the standard FRW, right? It doesn't really matter what happened at very early in the history of the universe because most of the contribution comes from the late time.
But I guess we're going to solve this problem using lambda.
Yes, exactly. But you have to change the actual evolution, the FRW.
So this computation is done using
Standard FRW, right? You assume that the universe is matter dominated today. Okay, it's matter plus cosmological constant today. You evolve backward, right? At 10 to the minus 4, at lambda equal 10 to the minus 4, it becomes radiation dominated. And then you evolve it backwards. Okay? But if you assume that its standard radiation domination works, right? Then what happened earlier really doesn't matter very much because the contribution to this integral, right, from lambda small will be small. Yeah, because you can see lambda dot goes as 1 over lambda square, right? In radiation dominated, lambda dot goes on 1 over lambda square. So when you put lambda equal to 1 over lambda square, there's an extra factor of lambda prime in the numerator, right? So the small lambdas will not matter very much.
So if you assume radiation dominance in the beginning and then comes down to matter and cosmological dominance, using that computation, this is the number you get.
Exactly.
You're trying to correct for the initial radiation dominance.
Exactly.
So that's still a very small level value.
Yes. So
Very drastic has to happen.
yes. So between but small lambda, something drastic has to happen, right? Because you have to use small lambda to produce a sufficient amount of horizon distance. Right? So that is the problem.
That's because we can't correct it. We can't correct things at large lambda because we are at large lambda.
Yeah, and we already know the physics, right? Between last scattering and today, right? We believe that we understand the physics, right? And meaning it will not change drastically. Okay, so whatever is happening, right, would have definitely had to happen before Big Bang nucleosynthesis, right? Because that has that prediction also you have verified, right? And if we believe in standard model physics, right, it has to happen even before the standard model physics. Okay, so how to change the history of the universe? So we want large contribution to RH from some range of lambda. Say lambda 1 less than lambda 2. Some two values of lambda 1 and lambda 2, and let's suppose that between lambda 1 and lambda 2, right, something drastic happened and you got some large contribution to this integral, right? That will solve the problem, right? If you could engineer that will solve the problem, right? Because you need to add something to RH, right? Large enough contribution to RH. Is that clear? So let's see what you could do. So let's suppose that we have an equation of state P equal to W rho. Okay, it's not necessary that we take the equation of state this way, right? But let's just for simplification assume that the equation of state, that at some point that in between this, in this range, the equation of state took the form P equal to W times rho. W is a constant. Okay, so for example, W is 0 for matter, 1/3 for radiation, and -1 for cosmological constant.
How does it change the work from this range? So that 2 degree becomes.
Yes, so that it has to become sufficiently large so that the RH that you calculate should be at least 360. It can be much more than that, right? If it uniformizes much over a much greater distance, we don't mind, right? But it should at least be able to uniformize between here and here.
Speaking of, you should have quoted this as Hegelian.
As?
Isn't it a sphere? So you shouldn't have quoted this as Hegelian.
Well, you can do that, but I can take 2 points and it's in a plane. 2 points and the center always forms a plane, right?
Okay.
Yeah, so you can use steradian, but I mean, I'm just using 2 degree. You can take a circle, a disk with 2 degree diameter. Yeah. Okay, so we assume that you have an equation of state of this form, that somehow between lambda 1 and lambda 2, the equation of state got changed to P equal to W rho. Okay, the standard equation of state, radiation dominated, would have been P equal to 1/3 rho. Okay, so W in the standard radiation dominated universe, W would have been 1/3, right? Except during those times when some particles are going non-relativistic, right? In which case the equation this will not be the correct formula anymore, right? Because it's some particles are changing from radiation to matter. Okay, but those are small effects. So during this time we have ddt of rho lambda cube is equal to -3p lambda square lambda dot, right? So this gives you -3w rho lambda square lambda dot. Okay. and it's a simple exercise to check. This implies that d dt of rho times lambda to the 3 1 plus w equal to 0. Right? So rho lambda cube will give you this one. So you can write as d dt of rho lambda cube times lambda to the 3w. Right? When you differentiate rho lambda cube, you get this term. When you differentiate lambda to the 3w, you get this term. So this tells us the rho should fall off as some constant times lambda to the minus 3 times 1 plus w. So the Friedman equation now tells us that lambda dot over lambda, which is square root 8 pi g over 3 times rho, is square root 8 pi g over 3 times c times lambda to the power minus 3 by 2 times 1 plus w. Right? So lambda dot is lambda to the power is, then the constant is not really relevant, let me write it, gc over 3 times lambda to the minus half minus 3w by 2 So using that, we are going to calculate RH of lambda 2 minus RH of lambda 1. Okay, how much contribution do we get to RH between lambda 1 and lambda 2? Okay, assuming that lambda dot is given by a formula like this. Is clear? So this gives you, so 1 over lambda dot, right? So square root 3 over 8 pi gc integral lambda 1 to lambda 2 and d lambda prime. So lambda prime lambda dot. So lambda prime times lambda dot. So lambda dot will be lambda to the half minus 3w by 2. So lambda prime to the minus half plus 3w by 2. Right? How do you fix C? Well, we will see. I mean, right now we are just using some C. I mean, you have to basically fix C by energy conservation, right? Because after, when this process ends, that C, the energy densities have to match, right? You cannot suddenly change the energy. So when you go from, for example, this phase to the radiation dominated phase, or whichever phase you go into, the energy of this phase at lambda 2 should match the energy of radiation at lambda 2, right? So that's how we'll have to fix it. So this is square root of 3 over 8 pi gc, and then we get 2 over 3w plus 1 lambda to the power half plus 3w by 2 Is this clear? Now lambda 1 and lambda 2 are both small because it's happening in the early universe. So if lambda 1 and lambda 2 are both small, this quantity will be small as long as this exponent is positive. But if the exponent is negative, then you can get a large contribution by taking lambda 1 to be small, for example. Is that clear? Lambda 1 is smaller than lambda 2. Suppose the exponent is negative. Then there is overall minus sign because this will be negative. Okay. But importantly, this will become large.
How do you mention the overall minus sign?
Oh, well, because this will become now lambda 1 to this minus lambda 2 to this. See, you are integrating a positive quantity, so you cannot get negative quantity in any case, right? Yeah. So if this changes sign, then this becomes larger than this. Right? So there is no sign problem. Right? But this whole quantity you can make large if you assume that half plus 3w by 2 is negative. Right? So this can be made large, can be large for small lambda 1, lambda 2 if half plus 3w by 2 is negative, or this means w is less than minus 1/3. Well, the point is both are small anyway, because all of this is happening in the early universe, right? We start with lambda equal to 1 today, and this has to happen before, at least before Big Bang nucleosynthesis. So both are small anyway, but lambda 1 is smaller than lambda 2. Though you start from it's increasing, right? Lambda always increases, right? So lambda 1 is smaller than lambda 2.
Yeah, that's okay. But this lambda, about the lambda 2 value, if that is also small, then there will be, since that is also the 1 over lambda 2, that will have some compensation.
Yeah, true. But lambda 1 can be even smaller, right? So you want lambda 1 and lambda 2 to be small enough. Lambda 2, as I said, it doesn't matter, right? But lambda 2 is, I mean, it cannot be too small, too big, right? Because it has to, all this has to happen before Big Bang nucleosynthesis, and it has to happen even before the baryon B minus L production, right? All of those has to happen after this inflation. Okay? So lambda 2, I mean, cannot be too large. Yes.
Are we assuming that lambda grows monotonically?
Yes. Yeah, we are assuming lambda grows monotonically with T. Right? But otherwise energy density has to go to 0, right? Because lambda dot over lambda has energy density on the right hand side. So if lambda has to turn around, right, then rho has to vanish at some point.
It has a square, right?
Yeah, it has a square. So lambda has to pass through, lambda dot has to pass through 0 to in order to become negative, right? Unless it jumps discontinuously. Right? So a continuous change of lambda dot from positive to negative requires that it has to go through 0, and hence rho has to vanish.
Here we are assuming that some species is dominant, right?
Some, yes, we are assuming that some species is dominating. In general, you can take mixture, that will just make life more complicated.
Only cosmological constant has less than or minus.
Among the known ones, only cosmological constant has less than 1, less than 0. Right? And that's the commonly used procedure, commonly used thing in inflation, but it's not necessary. And in fact, we will see that in this flow roll inflation, it's not really that W is constant. Yeah, W can actually change with time. Okay, but in this rough picture, this is the physics, that if we somehow take W to be less than minus 1/3, it is possible to add large number to RH in early universe.
So cosmological constant dominance will be sufficient.
Yeah, so cosmological constant dominance will be sufficient. So this can be achieved by cosmological constant dominance. But a cosmological constant cannot dominate, because we don't want cosmological constant by definition is a constant, right? And we cannot have a constant dominating because we know that at the time of Big Bang neutron, the nucleosynthesis, certainly cosmological constant was not dominating, right? If the cosmological constant was dominating, right, and it was constant, then it will always dominate, right? Because once the cosmological constant starts dominating, it grows, everything else gets diluted, right? As you have seen, radiation, matter, so it will never catch up. Okay. So it cannot really be cosmological constant. Okay. But the way this is framed, this is formulated, is that you have a scalar field, right? Imagine that you have a scalar field with a potential which has a flat region. Okay, we will see later that it's not really necessary to have a strictly flat region of the potential. Okay, but imagine this is the extreme case, that a scalar field with a region which has a flat potential, maybe slowly rolling, sloping towards the right, but it has a flat potential. And imagine that the scalar field in the universe started evolving, right, and it is somewhere here. So this will follow the same equation, right? Phi double dot y plus 3h phi dot plus b prime phi equal to 0 if grad phi equal to 0.
There we put grad phi equal to 0 because inflation.
Yeah, true. I'm coming to that, right? That here you have to justify. Okay. But imagine for some reason that in some region, right? For some reason the grad phi was small, right? Maybe not strictly 0. In that case, phi will roll slowly. Okay. So what will be h, right? So energy density so rho would be half phi dot square minus d phi. T will be half phi dot square plus v phi. Okay. And phi dot is small because of a damping. Sorry, rho is plus, v is minus, thank you. So phi dot, for small phi dot, okay, because it is rolling slowly, right? Potential is almost flat, so the driving force is small, right? And there is a damping. For small phi dot, we see that rho is approximately v of phi, and p is approximately minus v of phi. So this is as if it's like a cosmological constant, right? Cosmological constant is p, rho equal to lambda, p equal to minus lambda.
You are suggesting some new species.
Yes, some new scalar field. So this is what is called the inflaton. And once it starts inflating, so then the universe will start expanding exponentially, right? Once it starts expanding exponentially, then grad phi goes to 0. Okay. So if we can find some region of the universe where grad phi was small, right? Maybe not 0, but small, right? Then rho and p to begin with was not exactly of this form. It was close to cosmological constant, but there are corrections. Okay. But once the effect of that starts expanding the universe, right, then grad phi becomes rapidly goes to 0, right? Because the universe expands exponentially, right? If you remember, for cosmological constant, lambda goes as exponential h times t, right? H is constant in that case. H is constant, and the value of h is basically square root of 8 pi g over 3 times v of phi. So the picture is that the field rolls like this, right? It's phi dot is 0, but not quite 0 because there is a small slope. So v prime phi is driving it, right? So it rolls for a long time. During that time, the universe inflates exponentially. Yeah, and one can show that you need, if you can get about 60 folding, right? If it can expand exponentially 60 times, not 60 times, e to the 60 times, okay? Then you can solve the horizon problem. Okay, so you need a large amount of expansion, but as long as you can do 60 folding, you solve the horizon problem. Okay, you add enough to RH to span that 360 whole 360 degree. And then once the scalar field comes here, then it starts rolling down, right? It starts oscillating around the minimum. And as you saw, oscillation around the minimum can be effectively will correspond to matter. Pressure will go to 0, average pressure will go to 0, same physics as the axionic dark matter. It's after all a scalar field oscillating around its minimum, right? So P will average to 0, rho will average to non-zero value. And this can then be reinterpreted as saying that the original energy density that was stored in here gets converted to large number of highly non-relativistic phi particle, because phi particle has some mass around this, right? The second derivative of the potential around this point will give the mass square of the phi particle. Okay. So whatever energy was stored, right, at the end of an inflation, it gets converted to matter in the form of large number of phi particles.
But then you should see these like
No, so then you have to also do more work, because that phi particle has to couple to the standard model particles, so that because they are massive phi particles, they will eventually decay into standard model particles in the form of radiation. Right? At this energy scale, right, the standard model particles are all relativistic. Relativistic, right? So then it goes from the cosmological constant dominated era to matter dominated. When this, so this is called the reheating. Okay, because the universe became cold here, right? Because as lambda expanded exponentially, temperature dropped exponentially, right? T goes as 1 over lambda. So the temperature of the universe became almost 0 in this region, right? So here, that temperature got converted to matter, that energy density got converted to matter, and then the matter got converted to radiation by decay into massless particles. Because it was 0 here, temperature, it can start with a high temperature, right? But once the inflation started, right, T falls as 1 over lambda, right? So if lambda gets multiplied by e to the 60, T will get multiplied by e to the minus 60, right? So the temperature becomes 0, right? But in this region, that energy density got eventually converted to radiation and gave non-zero energy density.
the energy density of the phi, of the inflaton.
Inflaton, and then eventually it decays into standard model particles.
I'm asking, during the heating phase, the energy density of the inflaton you're saying gets converted into something.
Yeah, so exactly. So the phi is oscillating, right? Here. Now the point, because the phi couples to the standard model particles, right? It will start decaying, right? So that will appear as a damped oscillation, right? Because the phi amplitude will start reducing. The number of phi particles is going down, right? Because phi is eventually decaying into the standard model particles. Okay? So this reheating process is this whole process, the oscillation of phi and getting eventually settling down to 0. Right? So there's a phi particle left over. All the energy of the phi particle is getting converted to the radiation. Right?
And this grad phi goes to 0 is the question.
Yes.
How did you justify it? But
Oh, because once, suppose it was not 0 but small to begin with. Yeah, some region of the universe had some small grad phi. Okay. Then it will behave like approximately cosmological constant, right? The extra terms will be small, right? Not 0. Right? Once it has approximate cosmological constant, it will start expanding exponentially, right? And once it starts expanding exponentially, it gets smoothened out, right? Grad phi becomes smaller and smaller. So that is the basic idea of the scalar field driven inflation. That it reinforces itself, that even if you find some region, right, some random region in the universe where grad phi was small, right, that region will start inflating.
what if it was uniformly spatially non-convergent?
Well, uniformly spatial and non-homogeneous will be hard to achieve, right? I mean, in a random universe, right? You start with a high temperature system, right? Phi is fluctuating, right? Just thermal fluctuation. There will always be some region where the fluctuation is small, right? There is a distribution of what grad phi, the probability distribution for grad phi taking various values, right? As long as there is some region where grad phi is small, okay, that region can start expanding, start inflating.
What's the argument from homogeneity that translation?
From homogeneity.
Yeah, because
But we are trying to explain why homogeneity, right? That if you start with a universe which is at hot, right? You don't know anything about homogeneity, right? You need some region where grad phi was small, right? And the point is, it could be some random region, right? It just happened that grad phi was small. And once you have such a region, then it will start expanding. Yes, that's right. So phi has to, so if it was dark matter candidate, you have to have very weak coupling to a standard model particles, right? Then the reheating process will slow down, right? And by the time the universe gets reheated, right, the temperature will come down. See, temperature is falling anyway, right? Because the universe is expanding, right? It's not falling exponentially, but it's still falling as 1 over lambda, right? So the temperature is going down, and you want to make sure that the temperature doesn't go down too much, that we cannot have Big Bang nucleosynthesis or the B minus L production, etc., right? So you want somewhat efficient reheating process, right, where the phi quickly transfers its energy to the standard model particles.
And this is before, this is for small lambda, before nucleus.
Yes, so the final lambda is here, right? Maybe there is a small value of the potential that is describing the lambda that is today, right? This process is happening before Big Bang nucleosynthesis and everything else that happened, right? So at the end of this process, so you want the temperature to be raised to sufficiently high value, right, so that all those things can happen, right? It should be, for example, at least 1 MeV for Big Bang nucleosynthesis to happen, right? If you want to produce B minus L, right, it has to be more than 100 GeV, right? If maybe 10 to the 5 to 10 to the 6 GeV. Okay. So temperature has to be above that, right? Otherwise, there is no scope of producing B minus L by this leptogenesis process, right?
How does this scalar couple to standard model?
Well, there are various models, right? It has to couple to at least one particle in the standard. It doesn't have to couple to everything. As long as it couples to something, right, that something will decay into the other particles, then thermal equilibrium will establish, right? Because at this temperature, if the temperature is high enough, then the standard model physics is in thermal equilibrium, right? So as long as it produces one particle, right, maybe it will produce Higgs, for example, right? Then Higgs will go into other particles. Well, if we can produce energies of this kind, right, that depends on what energy scale inflation took place, right? The original proposal was at 10 to the 16 GeV, right? So that you cannot really observe, 16 GeV, right? But that proposal again was motivated because grand unified theories had that scale, right, 10 to the 16 GeV, right? Because people are trying to say that inflaton is one of the fields from the grand unified theory, right? But if you give up grand unified theory, right, if you don't want that, then inflaton could, this can happen at a lower scale, right? So from the experimental viewpoint, right, the only bound on the scale of inflation is that it has to be at a sufficiently high scale, right, so that after reheating the temperature is raised to do all the things that you want to do, right? The B minus L production, we've done nucleosynthesis and everything else.
By grand unified, you mean you want to write like one size?
Yeah, like one SU5 group that contains all the standard model group, for example, right? So that scale we saw was about 10 to the 16 GeV.
So there is no restriction on the phi being some representation of the standard model.
It could be a scalar.
But scalar in some representation? Oh, it's just one
Scalar,
scalar.
yeah.
It's just one scalar.
Yeah, neutral. Right? Normally one takes this to be neutral.
Some real scalar.
Yeah, some real scalar. Yeah, but there are various versions of this. Yeah, this is the simplest one. Take one real scalar and put a potential of this kind.
if you appropriately model it, it is possible to produce some baryon symmetry also, some more baryons that are given.
Possible in principle, so you can use some of phi to couple to produce baryons, right? I don't know whether people have written down models of that kind, where during the reheating itself you produce more baryons than antibaryons or something like that.
Electroweak physics won't affect phi, but because that comes after. I'm just wondering.
If phi is neutral under the standard model gauge group, then it doesn't have direct electroweak interaction, right?
Yeah, but let's say I wrote down a model where phi is charged under the SU.
Oh, then it will affect, yes. There will be a heavy particle which is charged, for example, right?
Yeah, I'm just wondering how the SU2 breaking, the electroweak breaking will affect the.
Oh, you have to make sure the phi potential is such that the minimum of the potential doesn't break electroweak symmetry. Right? This point, right, should correspond to phi equal to 0. Typically, we don't take phi to be electroweak charged, right? That puts much more constraint because we don't want the electroweak symmetry to be broken at that scale, right?
So I was looking for something similar. Electroweak symmetry breaking will happen at some 100 GeV something, with the Higgs, etc. But how will that affect the phi when the phi goes down there to 200 GeV?
But phi will be very heavy. I mean, this slope has to be reasonably heavy. The phi mass has to be large, right? So it will be like a very, very heavy scalar which has decoupled, right? You don't worry about this at the electroweak symmetry breaking scale. Yeah, it looks from this physics that you have to very narrowly fine-tune things, right? But we will see next time, or maybe at some time, that even just m square phi square will do the job. Right? You don't really need this highly fine-tuned kind of potential. Right? That's a simple polynomial, right? Simplest is m square phi square or lambda phi to the 4. Right? Even that is enough to produce inflation.
What about the slow roll?
It will happen. Even with m square phi square, it will happen. Right? That there will be region in the phi parameters, in the phi range, where it will act as if it's slow roll.
The slowness of the rolling was covered by that phi equals 0, right?
Also, v prime phi equal to 0. Because v prime phi is the driving force, right? Right? So these had to be small, so that
And you are saying, I mean, for m square phi square equals 0,
this can happen, yeah. Because when you say it has to be small, it has to be small compared to something, right? That it has this process has to last sufficiently long so that you have enough number of e-folding, right? And that part you can also achieve just with m square phi square, right? Or simple polynomial phi to the p, right? Yes.
Linear also will work?
Linear, okay, linear I don't know. I think I have given a homework problem which is part of it is linear, but it's not totally completely linear.
I was thinking like P.
Yeah, well, you can try. As long as the slope is small enough, you can probably do it. Right? So, because the point is that a lot of players, right? I mean, this is a very simple picture, right? Where it should really act like as a cosmological constant. But as you saw, we really don't need this, right? Because as long as W is less than -1/3, it will do the job, right? So you don't even think in terms of this anymore, right? When you solve the equations, we write down the Einstein's theory coupled to gravity, right? This equation. Okay, and assume that V is lambda phi to the p.
More than that, there are spatial derivatives.
Well, spatial derivatives will go away as long as the thing inflates, right? It will go away. Okay, because it's basically rapid expansion that's happening during this process, right? So this will be the main player equation of this kind, and you have to make sure that there is a range of this phi evolution during which the scale factor expands exponentially. Okay.
What was the energy scale acquisition of the states to this? 10 to the 16?
Well, that was the original proposal, 10 to the 16 GeV, right? But then there are other models where this happens at a lower scale, right? So it is not fixed what energy scale you can do this. The only thing that you know is that the energy scale should be such that after reheating, the temperature gets raised to so that you can do B minus L asymmetry, right? Big bang necrosis, all of those things. Right? All the standard predictions of the cosmology, right? If you want to hold, you have to have sufficiently high energy scale, right? So that temperature gets raised above that, right? So that after that you can use the standard radiation dominated physics.
How far can we go, like, on a
How far can we?
probe energy scale?
Well, by sitting on the Earth, no, you cannot probably probe 10 to the 16 GeV. Right now, the LHC is running at 14 TeV, right? That is 14,000 GeV.
10 to the 12 electrons.
Yeah, in terms of GeV, it's like 10 to the 4 GeV, right? And this is talking about 10 to the 16 GeV. So you cannot certainly go that far, right? But then there are various early universe predictions. I mean, there will be signatures of this in early universe, which you could see.
Signature in early universe, but maximum that we can go is gravitational waves, right?
Gravitational waves, of course, can be seen for very, very early universe, right?
Yeah.
All the way to the Planck scale, 10 to the 19 GeV. So if you can detect gravitational waves from the early universe, you can see even all the, in principle, all the way up to 10 to the 19 GeV.
But what about, like, as in the case of photons, we had scattering with particles. In the case of gravitational waves, if it
All scattering will be gravitational interaction strength, right? And that's very, very low.
yeah.
So of course it scatters with particles, but that interaction strength, right, is 10 to the minus 36 times the photon interaction strength. So gravitational wave, you can think of the universe as being transparent to gravitational waves.
Yeah. And in the early universe, there was not, no, in the very early universe, there were dense.
Yeah, but that is not, I mean, strong enough to scatter gravitational waves, right? The density has to be of the order of the Planck scale. That's 10 to the 19 GeV.
Okay. That will produce, like, how much, how much noise?
How much noise?
I mean to say, you have a photon. So, okay, so suppose we analogously say there is some sigma v for gravitational waves.